All right, ladies and gentlemen, AP, we're going to make sure that you're really clear on what you remember about inertia and Newton's first law from your ninth grade physics class. So um, Galileo came up with the idea of inertia, and inertia means is related to an object's resistance to its change in its state of motion or rest. Um, and Newton built on that idea. So Newton said that an object that traveled in a straight line at a constant velocity will continue to move at the same speed and in the same direction unless an unbalanced force accelerates it. So that ball across the bottom kind of shows that idea. Likewise, an object that is at rest is going to stay at rest until an unbalanced force accelerates it. So Newton's first law is called the law of inertia, and it basically states that objects will continue doing whatever they are already doing unless an unbalanced force changes it. Here's a little video that you can watch if you want to click on this and go there. I'm going to skip it, but you're welcome to do that if you pull up this as a PowerPoint rather than as a movie. So Isaac Newton compiled his three laws of motion, and as I said, this first law is the law of inertia. And it said that an object that is in motion at constant velocity will stay in motion at constant velocity unless a next force acts on that object. Remember that constant velocity means constant speed and direction. So neither speed nor direction can change for velocity to remain constant. Similarly, if an object is at rest or the velocity is equal to zero, then that object is going to remain at rest until it's acted upon by an unbalanced force. To find net forces, the net force is the sum of all the forces acting on an object. This funny looking little sideways M is the Greek letter sigma, which means sum or add. And all we do is we add up all of those forces in a line. However, all these have to be collinear. So we can't add an up and down vector to a side to side vector without doing some resolution of those vectors. So whenever we do the sum of the forces like this, we're always doing them in a given direction. So all in the x direction or all in the y direction or all parallel to a surface or all perpendicular to a surface. And then we can resolve those perpendicular components if we need to, but that's a separate operation. Okay, so if we look at this, in the first one we have two applied forces, 5 newtons and 10 newtons, both in the same direction. So the net force is just 15 newtons in the direction of the initial 2. In the second example, we've got 5 newtons one way and 10 newtons the other way. Typically, when we look at a problem like this, we consider this direction to be positive and this direction to be negative. So we end up with a net force of 5 newtons in the direction that's to the right on the screen. Then on this last one, we have 5 newtons both to the right. So even though they're applied a little bit differently, if we put them both, if we indicate that they're both acting to the right, then we have a net force of 10 newtons to the right. Okay, so what happens if the net force on an object is 0? When the forces are balanced on an object, that means that the forces are canceled out. So if we have 10 newtons left, we have 10 newtons right. That means a net force of 10 newtons, and this is called a state of equilibrium. So when an object is at rest, it's in static equilibrium, and when it's in dynamic equilibrium, it is moving at constant velocity. So objects can be in equilibrium when they're at rest or when they're moving. But if an object is in equilibrium while it's moving, it must be moving at a constant velocity. Okay, so in this case, why does this mass not fall through the table? It's because we have the weight acting down and we have a normal force acting up. Those forces oppose one another and they are balanced. So this is a case of static equilibrium. The net force is 0. Okay, it's also super important to remember that the net force has to be 0 for Newton's first law to be applied or to show Newton's first law. So Newton's first law supports that requirement for balanced forces in an equilibrium state. Whenever forces are unbalanced, then we're dealing with Newton's second law. So when forces are balanced, then we have situations that are obeying Newton's first law. Um, and remember as well that when things are in equilibrium, they can either be at rest or moving at constant velocity. So equilibrium does not mean that the object is sitting still. It means it's either at rest or moving at a constant velocity. Super important to remember that. So unbalanced forces are unbalanced if the force in one direction is larger than the force in the opposite direction. So in this case, we would have unbalanced forces to the right of 3 newtons. So this object would be accelerating to the right. So this, because it creates a net force to the right of 3 newtons. Objects always accelerate in the direction of the net force. Always. So that's the reason for finding net forces, is because once we know a net force, we know the object is accelerating in the direction of that net force. Similarly, if we know an acceleration in a certain direction, then we can use that to find some unknown forces, because we will know that we have to have a certain net force in order to create the acceleration that's involved. But we'll get to that when we get to Newton's second law. And remember that things don't always move in the direction of acceleration. So for the example listed here, if the velocity of an object to the right is to the right and the acceleration is to the left, then that object will slow down. And if that leftward acceleration continues for a long enough period of time, the object that was initially moving to the right may slow down and stop, change direction, and then speed up toward the left. So, so don't fall into that trap of assuming that things move in the direction of acceleration. They do not. Always, always, always remember that. That's a piece of kinematics. So super important to remember that. Okay, good luck. Thank you for doing this.